In this video the impact of various circuit and signal parameters on the low-pass filter will be demonstrated. Let's see changes in the low-pass filter response as the value of the resistor is modified with constant values of capacitor at 0.01 microfarad, and input signal sine wave of peak-to-peak amplitude at 2 volt peak-to-peak at a frequency of 500 Hz. With resistor value equal to 1 kilo ohm, the cutoff frequency of the low-pass filter 15.9 kHz. Since the input frequency is 500 Hz, lies in the passband region of the filter, the time response in the oscilloscope shows the output voltage is 2 volt, that is same as the input signal amplitude. It's also interesting to observe that output signal of the filter is in phase with the input signal. Now as the resistance is changed to 10 kilo ohm, the cutoff frequency of the filter reduces to 1.59 Hz. Since the input signal frequency 500 Hz is closer to cutoff frequency, the output signal amplitude reduces to 1.86 volt and the output signal's phases lags compared to input signal. Now have a look at the changes in the low-pass filter response as the value of the capacitor is modified by keeping the resistor value constant at parallel combination of 1 kilo ohm and 10 kilo ohm, that is equal to 909 ohm. Input sine wave of peak-to-peak amplitude at 2 volt and frequency at 2 kHz. With capacitor value equal to 0.1 microfarad, the cutoff frequency of the low-pass filter 1.75 kHz. Since the input frequency is 2 kHz, which is more than the cutoff frequency, the time response in the oscilloscope shows the output voltage peak-to-peak amplitude is 1.4 volt, which is lesser than the input signal. It's also interesting to observe that phase of the output signal lags more than 45 degrees compared to that of the input signal. Now as the capacitor is changed to 0.01 microfarad, the cutoff frequency increases to 17.5 kHz. Since the input signal frequency 2 kHz is very less than cutoff frequency and lies in the passband of the filter, therefore the output signal amplitude is 2 volt, same as that of the input signal, and both waveforms are in phase. Let's see the impact of signal frequency on the low-pass filter response by keeping the value of the resistor, capacitor constant at 10 kilo ohm and 0.01 microfarad respectively. Input sine wave of peak-to-peak amplitude at 2 volt. The cutoff frequency of the low-pass filter is 1.59 kHz. First, with input signal at 100 Hz, the oscilloscope shows the output signal peak-to-peak amplitude of 2 volt. As the frequency increases to 500 Hz, the output amplitude reduces to 1.86 volt and it further reduces to 1.56 volt as the frequency reaches 1 kHz. If the frequency further increases to 2 kHz, the time response shows that output amplitude becoming 1 volt, and if the input frequency further increased to 4 kHz, which happens to be still more than the cutoff frequency of the filter, the output amplitude reduces to 660 mV, and it's interesting to observe that as the frequency increases, the phase of output signal lags more and more in comparison to the input signal. After observing the time response of the low-pass filter, now let's have a look at the impact of resistor value on the frequency response of the low-pass filter. The capacitor value is kept constant at 0.1 microfarad and the input amplitude is kept at 1 volt. With resistance of 1 kilo ohm, the bode plot shows the passband gain of almost 0 dB at 220 Hz and the 3 dB cutoff frequency is 1.79 kHz against the ideal expected value of 1.59 kHz. One of the important characteristics of the filter that is roll-off is minus 18.9 dB per decade. If the value of resistor is changed to 10 kilo ohm, passband gain measured at 34.9 Hz is again almost 0 dB and the cutoff frequency is 180 Hz against the ideal value of 159 Hz. The roll off the filter is minus 18.69 dB per decade. It's also noticeable that phase difference between output and input signal in the passband is close to 0 degree, and at the cutoff frequency it is minus 45 degree. Subscribe to Labsland to explore many more parametric analysis of low-pass filter.